Hello, dear friends. This is Mechanical Vibration Lecture 4. It is all about free vibration analysis of damped single degree of freedom system. So we'll see this topic today. So what are damped vibrations? As we see from here, how do they differ from free vibration? These are some questions to start or to begin the lecture. So harmonic oscillations tends to die away as time goes on. This behavior called damping of the oscillation when it is produced by forces such as friction force, that air friction, viscosity. The forces are collectively known as dissipative forces because they tend to dissipate the potential and kinetic energy of the oscillating bodies into the energy of quadratic motions of atoms and the molecules. That is known as heat. So most of the time, the energies are absorbed in the form of heat or sound. So damped vibration means when the energy of vibrating system is gradually dissipated by friction and other resistance, the vibrations are said to be damped. The vibrations gradually reduce or change in the frequency or intensity or ceases as the system rests in its equilibrium position. So damped free vibration of single degree of freedom system. The objective of this today's lecture is to understand the damping as a force resisting motion, adding viscous damping to the equation of motion of single degree of freedom, as we have discussed in the previous lectures. Understand the difference in the response of different systems depending on the values of damping. So this is a symbol to viscous damping. General assumptions are required in the modeling of damped free vibrations of single degree of freedom system are the spring mass damper system, in which the spring has no damping or no mass. The mass has no stiffness or no damping. The damper has no stiffness or mass. So that is one of an important assumption. Another, further, the mass is allowed to move in one direction only. That's why we call it as single degree of freedom. If it is move only in one direction, then it is single degree of freedom. Mechanisms of damping. So damping may be introduced into structures through diverse mechanisms. That includes linear viscous damping, non-linear viscous damping, viscoelastic damping, friction damping, and plastic deformation. Okay. We'll see a linear viscous damping case in current presentation, in which the damping force Fd is proportional to the velocity. That means Fd is equals to Cx dot. Cx dot is the velocity. C is the damping constant. Damping is some form of friction. In this case, when we consider damping here, it is some form of friction force. So in solid, friction between molecules results in damping. In fluid, viscosity is the form of damping that is most observed. In viscous damping model, damping is proportional to the velocity, which is we can observe it in the parallel plate theory of fluid analysis. So it is given in the form of Fc is equal to Cx of t, which with the constant C has units of Newton second per meter or kilogram per second. So we can see this shock absorber system. It consists of some these piston mechanisms. There is a cylinder here, and then there is a piston. There is a liquid or viscous fluid is inside of a cylinder. So the piston is pushing against the viscous fluid. And on the piston, there is some orifice which allows the flow of fluid from inside. So this is some example of the shock absorber. These are also some shock absorber systems in some vehicle system, like in motor vehicle and others. This is the statement which you have seen there. So this Zeta, or the friction, the shear force, which is proportional to the friction coefficient of mu. So as we see from here, this is common phenomena in the analysis of fluid. So everyone who has good background in fluid dynamics can understand this. These are the two parallel plates. One of the plate is considered stationary, and another one is moving against the stationary one. And there is a velocity profile will produce or resulted here. This is velocity profile. And this is the thickness of the viscous fluid in between two plates. So this is the movable plate. So this is known in the case of fluid dynamics. So again, this is another the same thing which we have seen in the previous slide. There is a cylinder with diameter d. There is a piston, so there is a piston with thickness t, and there is a small clearance for the in between piston and the cylinder, and there is also viscous media here. Here there is a viscous media or viscous fluid. So this can be related with here it is shear force. The shear stress is proportional to the friction times dv over dz. This is the velocity profile, a change in velocity over change in the thickness or in the z, which is when we consider the force is equals to shear force over shear area. So our shear area here is pi dt. Okay, so this is the shear force. Shear force is equals the force is equals to shear force times shear area, because stress is equals to force over area. So force is equal to stress times area. And from this relation, we can see the constant is pi dt mu over delta is the C value. That is the damping values, constant damping values. Okay, so which is Newton second per meter. So damping force is proportional to velocity, and damping coefficient C times velocity. So dx dt, we represent it as x dot, dissipates energy. So dashpots can be designed as in shock absorber or an equivalent effect of energy dissipating capacity, determined from tests to find the values of the coefficient C. So general form of equations for damped single degree of freedom system. What we are going to see here is for general form of equation. That means including forced vibration and then we'll see the free vibration case. So this system consists of stiffness, spring stiffness or spring constant K, the viscous damping constant Cb, and mass M, and which is subjected to some force. So in this case, the system is called force single degree of freedom vibration. Okay, so this is the initial length of the spring mass, and then there is, when it is moved to some x distance, then that will be the initiation of vibration. So this is the free body diagram for the single mass spring and dashboard system. So using the Newton law, I just take a equilibrium condition here. Okay, so we have kx in this direction, cbx in this direction, and force is in this direction. So then the mass is accelerating, which is mx dot dot is in this direction. So minus k, because minus indicates that our coordinate system is xy coordinate system of the normal type. Okay, from left to right, positive, and from bottom to top, positive. So for that, minus qx minus cbx plus f of x is equal to mx dot dot is directly applying the Newton second law. Okay, now from this relation, finally we can get the equation of motion. That is mx dot dot t plus cx dot plus kx, which is equal to f of x is the equation of motion. And at the same time, we have to prescribe the initial conditions, the initial displacement of the mass and the initial excitation velocity of the mass, so which is given. So the resulting question, this is the general form of force a single degree of freedom vibration case. Okay, so the solution to the general single degree of freedom equation of motion is shown in the damped single degree of freedom system in the next slide. So let's see those. If all parameters that are mass, spring stiffness, and viscous damping are constant, then the ordinary differential equation that satisfies this condition have a characteristic equation. Okay? So we'll solve it in the use of characteristic equation method. So let's take free vibration case. The free vibration case, because the solution method for free vibration and the solution method for forced vibration are different. They have similarity, but due to the presence of excitation force, constant excitation force of the system, the equation which we obtain from forced vibration is non-homogeneous equation. The previous equation here we can see this one is non-homogeneous equation. So this non-homogeneous equation needs the solution for the non-homogeneous, that for f of t solution. The particular and general solutions are required, so that except that the solution methods are almost the same. Okay, here the spring mass system having a mass which is slide over frictionless surface. Okay, and this is considering the frame of reference or the equilibrium position of the mass. Then we can develop a free body diagram for this system. So force of friction, force due to spring constant K, force due to the damper or dashpot Fc. Again, the mass is sliding over a frictionless surface, so there is no contribution of friction to the normal force, so that mass times acceleration is in this direction. So directly applying these equations, what we can get is applying the Newton second law, we can get the governing general equation. So the equation of motion for this system is equals to is mx dot dot plus cx plus kx is equal to 0, because we have no excitation force here. Okay, so if there is no force, so it is a homogeneous equation type. Okay, this is homogeneous equation. Second order differential equation of homogeneous type, because f of x is equals to 0. And that's why it is called free vibration. If there is force, it is not free vibration, but it is forced vibration. Okay, so now let's divide the equation of motion this by both sides by m. Then we can get c over m x dot dot of t plus c over m x dot plus k over m x, which is equal to 0. So we have to define some terms which are very important here. In this case, some terms need definition. Some terms need some definition. So let's define the terms. Here, c over m is equal to 2 times zeta omega n, and k over m is equals to omega n squared. This omega n is the natural frequency. Zeta is the damping ratio. This zeta is the damping ratio, which is C over Cc. The damping constant C over the critical damping constant Cc, which is called zeta. Okay? That is damping ratio. So we introduce this defined terms in terms of the mass, or we can calculate as it. Okay, but let's simplify the equation into the new form, which is x dot dot plus 2 zeta omega n x dot plus omega n squared x. So this is one of the form of equation. Okay. Now, well, zeta is c over 2 omega nm, which is equals to c over radical of which is dimensionless constant. So that zeta is equals to c over cc. So it is directly defined from here. Okay. So let's consider x of t. Let's assume x of t is equals to a e lambda t. Be a solution for, because this equation is a homogeneous solution, a homogeneous equation of second order differential. Therefore, for such equation, we can assume either trigonometric relation, or we can assume exponential functions like this. So, sorry, if x of t is equals to a is arbitrary constant here, lambda is the eigenvalue that we can determine later. Okay, a is determined from the initial conditions, and the lambda is determined from the characteristic equation. So that x dot, from this relation we have x dot is equals to a lambda e lambda t, x dot dot is equals to a lambda square e lambda t. So by substituting these three equations, equation number 1, equation number 2, and the equation number 3, substituting these equations into this differential equation, finally what we can get, this, okay, a lambda square e lambda t plus a 2 zeta omega n lambda e lambda t plus a omega n square e lambda t. This is just substituting this equation into this. Finally, we can rearranging the terms. We have this equation. Here we have two terms. One of the term here in the inside of bracket, and another is here. So to exist this equation, this term should be different from 0. This term should be different from 0. If this is 0, all the equation becomes 0. So that there is no solution for. And the non-trivial solution will be obtained by equating this is equals to 0, which is the characteristic equation of the motion. This equation, which is equal to 0, implies this is characteristic equation. Okay, that A different from 0 here, A different from 0. And this equation is equal to 0. Okay. So m lambda square, this is characteristic equation, which is equal to 0. This is when we use the equation as it without substituting with defined terms. And this is in terms of defined terms. Okay, defined terms of the damping constant. So this is in terms of the constants of mass, the constant of dashpot, and the constant of stiffness. So I only representing both equations together here, just for your simple understanding. Okay. So in terms of the mass spring and dashpot constant, we have this equation. This equation indicates that lambda 1, 2, which is the solution for the quadratic equation. Okay, so because this one is a quadratic equation of the form ax plus ax squared plus bx plus c is equals to 0 type. It is similar to this. In our case, our A is M, our B is C, and our C is K. So just substituting those terms here, we can find the quadratic solution of this lambda. Again, for this equation, we have also here A is 1, okay, B is 2 zeta omega n, and C is omega n squared. So we substitute these values into this equation, because for such quadratic equation we have a solution of B is equals to x is equals to x1 2, because we have two roots for quadratic. X1 2 is equals to minus b plus or minus radical b square minus 4ac over 2b over 2a, sorry. This is over 2a. This is the equation. So in similar form, we substituted these values. Okay. Yeah. So these are the two solutions. Especially this one is the solution for lambda 1, 2. So lambda 1, 2 is equals to minus zeta omega n plus omega n radical of zeta square minus 1. This is this plus, for the plus one is the lambda 1, and the minus 1 is taken as lambda 2. Now, from the two roots of quadratic equation lambda 1, 2, that is the discriminant radical of c over 2m squared minus k over m, or radical of zeta square minus 1 in this case. This term, either this term or this term, which determines the nature of roots. In this case, we have 4 different cases in order to determine our system of equation. What are those things? Let's see. So for case of lambda 1 to c over 2m, okay, these are the actually solutions which you obtain. The first case is zeta is equals to 0. When zeta is equals to 0, what will happen? This term is 0. Again, this is 0. We have left only lambda 1 to lambda 1 2 is equals to plus or minus radical minus omega n, or plus or minus j omega n is left. This is the case which we have discussed in the previous lecture. That is the part of lecture 1. That is free vibration, undamped free vibration case. Okay, so this implies free oscillation that we already discussed in the previous case. Another case, when zeta is less than 1, the damping coefficient, which is damping coefficient of the damping constant over critical damping coefficient, less than 1. Actually, what do we mean by critical damping coefficient? Critical damping coefficient, Cc, implies that this C over 2m square minus k over m is equals to 0 condition. When this term is equals to this C is equals to the Cc1, that is called critical damping coefficient Cc. So this term, we can take this term in order to evaluate that critical damping coefficient. So that implies C square minus 4mk less than 0. Again, we can define these terms also. That is called underdamped vibration case. And another one is zeta is equals to 1. Zeta is equals to 1 means a critical damped condition. That means Cc is equals to C. Okay? C square minus 4mk is equals to 0. That is called critically damped vibration case. And another, the last one is zeta greater than 1, or C square minus 4mk greater than 0, which implies over damped vibration case. So let's see this each case. Okay. So in the case of critically damped, in the case of underdamped case, the roots of the characteristic equations, this equation. Let me show you the characteristic equation. This is our characteristic equation. Okay. The roots for these characteristic equations determines our analysis type. So the roots of the characteristic equation are complex conjugate form when these terms zeta is less than 1. Why? Because in the radical, when we see here radical, if this zeta is less than 1, that implies, for example, if we take 0.5, zeta value is equal to 0.5. 0.5 square is a smaller number than 1. That implies inside of radical, we can see some negative term. That implies the complex conjugate form of equation. So corresponding to the oscillatory motion with an exponentially decaying in the amplitude. How it's exponentially decaying? We'll see which term makes the amplitude decay exponentially. Another one is critical damped case, that is zeta is equals to 1 case. during this time, the roots of the characteristic equations are repeated. Root lambda 1 is equal to lambda 2. That implies a repeated roots, which corresponds to simple decaying motion with at most one overshoot of the system's resting position. In this case, it cannot go cycles. It cannot make a number of cycles. It will not oscillate, like in the case of free vibration and undamped free vibration and what we call underdamped vibration case. It will not make a repeated kind of cyclic motion, but it will go for once overshoot and then goes straight. Another overdamped case, the roots of characteristic curves are pure, real, and distinct. So this is the case in which the corresponding exponential decays, decaying motion is happening. So let's see one by one. The first and the most important case is underdamped case. When the system is underdamped, zeta value is less than 1. During this time, the characteristic equation gives us a pair of complex conjugate roots. These roots are here because zeta is less than 1, so that we multiply it by -1. And finally, what we can get, these are the roots. From here, lambda 1 is minus zeta plus j. J is the complex conjugate representation here, which implies the term -1 in the radical, which is equals to j. Sometimes we can represent it with I or j. So this is lambda 1, that is zeta minus zeta plus j radical 1 minus zeta square as a whole omega n. And lambda 2 is equals to, this is lambda 2. Lambda 2 is equals to minus zeta minus j radical of 1 minus zeta square times omega n are the two roots. Okay, one root and this is two roots. The displacement solution for this kind of system is we substitute, we have this x of t is equals to a1 e lambda 1 t plus a2, this is a2 e lambda 2t. This a1 and a2 are arbitrary constants, which we can determine them from initial conditions. So lambda 1 is the characteristic equation solution for the characteristic equation. Okay, the root of the characteristic equation. So we introduce lambda 1 here and lambda 2 here. So it becomes we can find this type of equation. Okay, so once we introduce them, let's multiply this term e the power of minus zeta omega n t, because in the exponential function we have e the power of let it be e the power of a plus b. A plus b is equals to x to the power of a times x to the power of b. We can represent like this. So here we have two terms, zeta plus j radical 1 minus zeta omega square. Nt is common for both. So let's take out this part. This is taken out. And this part also minus zeta omega n is nt is taken out here. and we multiply them with, it is this term. So this is the equation. So finally, here it is similar term, E minus zeta omega nt. Okay, here also e is a power of minus zeta omega nt. So let's take out this e is a power of minus zeta omega nt out. So it becomes e is a power of minus zeta omega nt the whole times a1 e j radical is a power of j radical 1 minus zeta square omega nt plus a2 e minus j. This is minus j, this one is plus j. So the power of radical 1 minus zeta square omega nt. This is the equation. I double strike is given for this equation because further we see this equation again. So alternatively, how we can represent this equation? Yeah, omega d represents the damped natural frequency of the system. For damped system, the damped frequency is called damped natural frequency, which is equivalent with omega n radical 1 minus zeta square. So rather than using these terms, omega n radical of 1 minus zeta square replaced by omega d. So here omega d is replaced. So that is defined like this. Now, once we get this equation, let's use the Euler expression for the relation between the cosine and sine terms with the exponential term. So according to Euler equation, e is a power of ja implies cos a plus j sine a, and e is a power of minus ja is equals to cos a minus j sine a. So let's use this relation for our these terms. Okay. So let's consider, let's take this and this in the cos sine or trigonometric form. So which is equals to only this terms inside the bracket. Okay. The terms inside brackets are defined a1 cos omega dt plus j sine omega dt plus a2 cos omega dt minus j sine omega dt. So this is this term, and this implies another this term. Okay. Now substituting these values into the equation and rearranging these cos terms and sine terms together. Here a1 cos omega dt, here a2 cos omega t. We add up them. Superposing these two, we can get a1 plus a2 cos omega dt. And the sine term j sine omega dt here a2 j sine omega dt. So that is j a1 minus a2 sine omega dt. So this also another equivalent representation. So let's assign a1 prime and a2 prime for instead of a1 minus a2 and a1 plus a2. For this, we have actually a good relation that shows how we can define this. Actually, we have already discussed in the previous lecture about this mathematical concept. So someone can refer the previous lecture for defining a1 prime and a2 prime. Okay. So now our equation we used only the term inside of the bracket only. These bracket terms are already defined here. So let's multiply it by this constant A, E minus zeta omega nt. By defining this A1 and A2 as to some degree of let's it be this A is equals to this A is equals to A1 prime square plus A2 prime square So by defining this term, substituting this into here, okay, A times E minus zeta omega nt times sine omega dt plus pi. Or in terms of cosine, we can define the solution like this. Or in terms of sine. So the terms here, this term is the exponential term, and this is periodic term. Okay, this is a periodic term and exponential terms. Okay. So the maximum amplitude and the phase angle for this is calculated from initial conditions. So let x of t is equal to 0 is equal to x naught, and x dot of t is equals to 0 is equals to x naught, or let it be v naught. So substituting these equations into our main equation here, what we can get, x naught is equal a1 prime is equals to x naught, and just differentiating this term once, we can get x dot. So substitute the x dot initial condition to this equation. Finally, we can get x naught dot is equals to minus zeta omega n a1 prime plus omega d a2 prime. A1 prime is already obtained, x naught, so we can easily find a2. Okay. A2 is equals to x naught dot plus zeta omega n x naught over omega d. Okay, so now A, the maximum amplitude is equals to A1 prime square plus A2 prime square, which gives us this equation. And after simplification, we can get maximum amplitude of vibration A as this equation. Okay, so we can use here the right angle relation of and application of Pythagoras theorem. Okay. The phase angle phi of vibration is obtained from this relation. So pi is equal to tan inverse of x naught omega d over x naught dot plus zeta omega x naught. Okay, this is the relation. Now, substituting these all terms into our equation of motion, what we finally get is either sine in terms of sine or cosine. We can get these equations. Okay. So the motion equation derived is damped harmonic motion of angular frequency omega d, which is equals to omega n times 1 minus under radical 1 minus zeta square. Because of the factor E minus omega nt is a power of minus omega nt, the amplitude decrease exponentially with time, as shown in the next figure. Look, in this figure, we have these terms, E minus omega nt. A is some constant, no problem. But this term makes as t increase, because this is minus is a power of minus omega zeta omega nt, means what? A times is a power of 1 over zeta omega nt. Zeta omega nt. As time increase, as time increase, this term decrease exponentially. So due to that, we can get such decreasing graph. We can see what is the amplitude decrement from this point to this, again from this to this. In every cycle of oscillation, what will be the amplitude decrement we can see. So here we see x1t, xt1, and xt2. At time t1, what is the amplitude? At time t2, what is the amplitude? So this will be discussed in the next. This is the equation of motion. Okay, so the equation of motion, x of t as a whole, we can see this solution. But the term a, e minus zeta omega nt produces this type of declining amplitude of the vibration. Okay, this is the frequency domain, which I am expressing the graph, and frequency domain, that is omega dt. Okay, one damped time period for damped vibrations, the time period is 2 pi over omega d, that is, and the relation between omega d over omega n versus zeta graph is here. At the very beginning, that means when there is no damping, means omega d 0 means that means, sorry, when zeta is 0, our omega d over omega n is equals to 1. And when zeta is 1, that is critically damped case, zeta is equals to zeta is equals to actually C over C critical. C critical. So that the critical value is equals to 1 means C is equals to CC. Then omega d over omega n is equals to it is 0 here. So this is the relation, the variation between damping constant, damping ratio, and the ratio of frequency. Now, another important concept here in the analysis of underdamped case is knowing the amplitude decrement from every successive period of decrement. For example, TD here, 2 TD, 3 TD means time for damped vibration, the time period for damped vibration, this TD implies. So what will be this decrement? For example, from here to here, what will be the decrement? Here the amplitudes are not the same. As we see, here there is some amount of decrement of amplitude in one period of oscillation. From here to here, one complete oscillation. Again, from here to here, it is not the same. We can trace it back like this. You can see this difference. Again here, some difference like this. So what are those things that are called? We call it as logarithmic decrement. So logarithmic decrement is defined as the natural logarithm of the ratio of any successive amplitudes. Let T1 and the T2 be the times corresponding to two consecutive amplitudes measured in one cycle apart for an underdamped system. Using the following equation, we can, this is a general equation for underdamped vibration case, as we have derived previously. Okay, so the ratio xt1 over x of t2 is known as the logarithmic decrement. Let's displacement at t1, at time t1, let it be x1. x1 is equals to x is zeta omega nt cos omega dt1 minus pi. Again, for t2, let's find x2 is equals to x is zeta omega nt cos omega dt2 minus pi. Now, T2 is the sum of T1 plus 1 time period. Okay. Here, 2 pi over omega d is 1 time period. So T2 is equal to T1 plus Td. Okay, that's substituted here. Then x2 is equals to, after this rearranging this system, we can get xe minus zeta omega nt2 times cos omega dt plus t1 plus 2, because now our terms is changed to t1 term. That is easy for us to evaluate. The same form, plus 2 pi minus pi. That is the second amplitude. Okay, so this is the second one. Okay, 1 and 2 are two successive amplitude equations. Now x1 over x2 gives us this over this. Okay. Another thing which I want to explain here is cos omega dt 1 plus 2 pi minus pi, which is equals to this 2 pi will be, when we multiply this, immediately this will be taken out from this system. That is a trigonometric relation of, for example, cos of alpha plus theta, which is equals to cos alpha cos theta plus minus sin alpha sin theta. Cos of alpha minus theta, cos alpha cos theta minus, if it is plus, it is minus, then it is minus, it is plus. This relation will, that cos of 2 pi is, that is 1, sine of 2 pi is 0, so the sine term will taken out away. So we have left only the cos term, which is cos 2 pi is cos, it is 1. So we have left for amplitude 1, x e minus zeta e the power of minus zeta omega nt1 cos omega dt 1 minus pi over x times e the power of minus omega nt cos omega dt2 minus pi, which implies we can remove these constant terms. Okay. These constant terms will be removed. Okay. So some rearrangements required here. Okay. Finally, we get x1 over x2 is equals to e the power of minus zeta omega nt1 over e the power of minus zeta omega nt1 plus zeta omega ntd. Still, further going, we will finally get e zeta omega ntd. Now the logarithm decrement delta, which is equals to the natural logarithm ln of x1 over x2. Delta is equals to ln of x1 over x2. So which gives us ln of this term. Ln of e the power of zeta omega ntd td. So finally, it gives us zeta omega n td. But using the critical damping And other terms, again, also someone can represent this in terms of the omega n. This means omega n radical of 1 minus zeta square. So we can represent it like this. Yeah. So this is the logarithmic decrement of the amplitude. So our delta is equals to 2 pi zeta over radical 1 minus zeta square. This is what we derive. For a small damping, zeta is too much less than 1. The equation delta is equal to ln of x1 over x2, which is equals to 2 pi zeta radical 1 minus zeta square, which can be approximated as delta is equal to 2 pi zeta. For zeta, too much less than 1. Okay? So we can see the delta versus zeta plot. Okay, here for very small value of zeta, about, for example, in near to 0, 1, 0.1, 0.2, 0.3, there the graph of zeta are almost coincide to each other here. Okay, they are coincided. So for the zeta versus the delta versus zeta plot, it can be noted that for values up to 0.3, the two curves are difficult to distinguish. Okay, so the logarithmic decrement delta is dimensionless and is actually another form of dimensionless damping ratio. Once delta is known, zeta can be found easily. We can solve them in this form. For very less value, we can use this equation. Okay, for normal zeta is equals to, so we can find zeta if we have given delta, or we can find delta if we have given zeta values. So this is the relation between them. So let's take one simple example on this point. So a single degree of mass damper spring system undergoes free damped vibration, which is relatively fast. A sensing system is utilized to measure the vibration amplitude, which can capture a successive data only every after 5 vibration cycles, whereby a constant decay of 50% is noted between two successive measurements. Determines the damping ratio that corresponds to these systems of vibration. So here what we have given is damped free vibration case, and the constant decay, that is delta value, is observed after every 5 successive amplitudes. We cannot observe it in the first cycle, second cycle, third cycle, but it is in the 5th cycle, which is 50% of constant decay of the amplitude is observed for this. Okay, so what we are going to determine is the damping ratio, zeta. What is zeta? So how we can calculate what is the solution? The ratio of two successive measured amplitude can be defined in this formula. So xk over xk plus 5 means this 5 is the n times the frequency, that 5 times the 5 cycles. This n is the cycle. So first cycle, second cycle, third cycle, fourth cycle, fifth cycle. So that's why we use this xk over xk plus 5. Actually, we cancel this all out, and we can finally get xk over x5. The remaining terms will cancel to each other. Okay. Now, applying the natural logarithm equation, we have ln of xk over x of xk plus 5, which is equal to 5 delta. This is already 5 delta means in every this cycle, not there, but here, this is delta. This is delta. Delta. Again, this is 1 delta, 1 delta. So the sum of these deltas gives us 5 delta. So according to the given data, sorry, let's go back. So 5 delta is equals to ln of xk over xk plus 5, okay, which is equals to x delta. Let's take this term and go to the next equation. So xk over xk plus 5 is equal to 1 over 0.5. This means 2. Xk over xk plus 5. This, after fifth successive amplitude, the ratio is equals to 2. 1, that is xk1. This one reduced to half, so we can get this value. So ln of this value is equals to 0.693. Ln of that. And ln of xk over xk plus 5 is equal to 5 delta. We have this equation from the previous equation. Okay, this is from the previous. So this value is equals to 0.693. So 0.693 is equals to 5, means delta is equals to what? 0.139. That is 0.693 over 5, which is 0.139. That is delta. Once we know delta, we have this relation. Zeta is equals to delta over radical of 2 pi as a whole square plus delta square. Substituting this, we can get zeta value. This implies zeta is underdamped case in which zeta value is very small. So this is all about underdamped vibration case. If we have sufficient time, or sometimes I may add some examples on every case. Now let's go to critically damped case. This is the case in which zeta is equal to 1 or C is equal to CC. Okay, so during this time, the characteristic question this has repeated roots, repeated real roots. That means lambda 1 and lambda 2 are the same. So such cases are special cases in the mathematics. So for such case, we have different solutions. Okay. So our zeta lambda 1, 2, which is minus c over 2m plus radical of c over 2m squared minus k, or in the special term, we can represent it like. So lambda 1 and the 2 are all the same. In this case, substitute the value of okay, we have this zeta is equals to 1. If we substitute zeta 1, this minus this produce this term 0. If this term is 0, we have left minus zeta omega n only. Okay. Because we substitute here zeta is equals to 1, 1 square is 1, 1 minus 1, 0. So this plus or minus term will be removed from the system. We have left minus zeta omega n. Again, zeta is 1. Then we have left only 1 omega n minus omega n. Okay, so this is both zeta 1 and the zeta of 2 are minus omega n, means they are it has only repeated roots. So the equation for this type is given in this form. In mathematics, for such kind of roots, we represent C1 plus C2t, unless it will not satisfy. Okay. So here we multiplied the equation, the constant by t, but here no t. So this is the form of equation which can satisfy the equation of repeated roots. And applying the initial conditions, finally we can get this equation. This is the equation for critically damped vibration case. So, sorry. Okay, the motion equation represented by this devil's plus sign is non-periodic. Since as e the power minus omega n t approaches to 0, t approaches to infinity. So this goes to infinity. So this is non-periodic type of motion. It immediately goes to some maximum amplitude and down within 1 period. Within 1 period, it comes to very less amplitude here, and then it is goes to infinity as the time marches. Okay, so this is the type of graph for critically damped vibration. So this is the equation of motion. Okay, so another is overdamped case. That is the third important case. In this case, zeta is greater than 1. Okay, this zeta is greater than 1. Or C, the damping coefficient is greater than the critically damping coefficient. And then it is termed as critically damped. And during this time, we have two distinct roots of lambda 1 and the lambda 2. There are two roots in this case. So lambda 1 and 2, which is minus zeta plus radical zeta square minus 1, omega n is lambda 1, and then minus zeta minus radical zeta square minus 1, omega n is another root. So our zeta is in this side, not in the opposite side this time. So the two roots are real roots, and they are not repeated and having no complex conjugate form. So this is the graph. Okay. In this case also, the graph maybe start from some x naught here. Okay, x naught here, and having some v naught here, goes to maximum amplitude, and then will not repeat also. In this equation also, the graph will not repeat. It is cycle. The positive root will have such decrement, and for the negative one, for this minus case, and here plus case are represented here. Okay, so this is overdamped vibration case. These are the two roots. We implement these roots into the equation. Okay, so the equation of this type. So applying this equation and also using the Euler formula, these roots will be expanded, or we can directly use it as it. Okay, so x of t is equals to a e lambda 1 t plus b e lambda 2 t. This a and the b are constants to be found from initial conditions, but the displacement initial conditions and the velocity initial conditions. So let me use, instead of a and the b, simply a1 and a2 here. Okay, a1 and a2. So x of t, x dot of t means the first derivative of the displacement. We can get this equation. Okay, when we derive this one first time, this whole terms comes to in front here, minus zeta plus radical of zeta square minus 1 omega n comes here, and is a power of minus zeta plus radical zeta square minus 1 omega n plus a2 minus zeta minus radical zeta square minus 1 omega n is a power of minus zeta minus radical square minus 1 the whole omega n. Now let's apply boundary condition, initial condition. So we can find A1 and A2 values. So applying those initial conditions, we can find A1 and A2 like. So A1 is equals to x naught minus x naught dot minus x naught omega n the whole zeta plus radical zeta square minus 1 over 2 omega n zeta square minus 1. And A2 is minus x naught dot minus x naught omega n as the whole zeta minus radical zeta square minus 1 over 2 omega n zeta square minus 1. These are two constants. Okay. The motion equation becomes, substituting these values, this is the constant which determines A1, and this is the constant A2. Substituting A1 and A2, we have this equation. This is long equation. Maybe if you will properly follow the steps, you can get it easily. But if you miss some mistake or make some mistake, then immediately the equation will get spoiled in some point. So be careful when you are deriving, derivating, and differentiating and applying boundary initial conditions. So the equation x of t is equals to a1 e zeta, the power of e zeta plus radical zeta square 1 or the whole omega n t plus a2 the power of minus zeta minus radical of zeta square minus 1 omega n. This shows that the motion is non-periodic regardless of the initial condition imposed to the system. So since the roots are both negative, the motion diminishes exponentially with time, as we can see from here. If it is slightly overdamped, means if the value of overdamped system zeta is equals to, for example, 2, zeta is equals to 5, zeta is equals to 10. So this time the graph goes like this. It becomes here it immediately comes to the first natural frequency. For example, this is the case of zeta is equals to 1. In the case of zeta is equals to 1, it comes down immediately and goes to infinity. But when zeta value increases, it goes like this. and goes like go like this. So this is the case for higher and higher zeta values. Okay. Let, for example, this is zeta is equals to 10. Let this be zeta is equals to 2. Let this be zeta is equals to 1. Actually, zeta 1, not 0. If zeta 0, there is a kind of motion which repeat on the time axis. So this is an approximation for very high zeta value. When zeta value is very high, this is the type of equation expected. Okay, so just to summarize this point, modeling viscous damping is have been seen. Driving equation of motion of viscous damped system is already we have seen. Solving the equation of motion involving viscous damping. Recognizing is a different type of responses based on the level of damping. So let's take a simple example or an assignment. Use a given data to plot the response of single degree of freedom system. Omega n is equal to 2 rad per second, x naught 1 millimeter, v naught 2 meter per second, for various value of zeta. Here, zeta 0.01, 0.1, 0.4, 0.8, 1, 2, 5. What is the plot? Actually, MATLAB program easily gives you beautiful curves of these zeta values. Okay. Again, solve the following differential equation. This is a differential equation, and these are initial conditions, and plot the response. Okay. So this is a homogeneous second order differential equation of the type what we have discussed in the damped free vibration case. Okay, so this is all about. Okay, we have some illustrative video lecture here. Let's see what the video. Sorry. This illustrative video lecture shows the 3 cases of damping: under damped case, critically damped case, and over damped case. 3 of the cases are presenting here. So the system initially vibrate from its equilibrium position. Let's see how it starts from. Yeah, this is the point where that equilibrium point. And then one of the systems is still vibrating. You see, it is still vibrating. Since it is underdamped. And the 2 are stopped immediately. That goes at the very beginning to the maximum amplitude, and then they stop without vibrating. So the critical damped case, it immediately overshoots and then stop. And over damped one, going stiffly and finally stop. So this is the case of the three vibration case. Yeah, this best describes the situation what we have learned. So look, the 3 cases are plotted here. So look, this is the underdamped vibration case. This underdamped vibration goes like this, finally diminish, and finally it vanishes. So it produces a kind of logarithmic decrement here from both sides like this. But when we go to critically damped one, we can see this green color here. The green color immediately comes here, then goes to infinity. Okay, so goes to infinity. But the red one, it goes to down like this, and stops just after some time period. It stops immediately. So this really plots illustrate this the condition of underdamped, critically damped, and overdamped case very nicely. So thank you very much. We'll see this thing more elaborated examples in the next. So thank you very much. This is all about today.